Please, we are happy to stay. Please stay if you want. But there are questions and we can chat.
And the 5-minute summary of the GAN. Just like, what's the high level intuition? Why should we be elevator picture?
Okay.
GAN.
Okay. Okay. So it's past 5. So you are don't feel sorry if you need to leave, but we will finish it in like hopefully.
One picture GAN and I can do one picture flow.
Yeah. Okay. So let's do the first slice of GAN. Oh, the GAN slide is a lot. Okay. So GAN is saying, hey, VAE or in VAE, these kind of likelihood function, they all suffer because we are solving the reconstruction error. And reconstruction error causes it to be blurred, right? Reconstruction error causes it to be blurred. Because why? Recall in VAE, the decoder is asked to generate or to fit 2 images from the exactly same data. And now GAN is challenging you. Hey, why bother learn the rules? Of course, from the rule you can generate, but is learning the rule the only way to generate? Or is learning the probability explicitly the only way to generate? He's saying that, hey, what do we want? All we want is just generating new realistic image. Right? I don't care if you can do some naughty things and give me a realistic image, even if you Google that and then saying that, okay, this is new image. As long as I haven't seen that, I'm happy, right? So this is what generator is doing. I train a neural network from a latent. So directly I train from prior. So I give a Gaussian sample from it, I train. Now the output, how do I know, how do I backpropagate, or how do I know whether my generator is good? I will have a critique network. This critique that we will discuss, I mean how it's go. But if this critique network can say, hey, this image is 76% real. This image is 15% real because it's blurred. Then I can backpropagate this back matrix in generator. And then I will learn that. Problem solved. So here you can see there's no maximum likelihood. Just this. I mean, at first sight, you will feel GAN must be proposed by some system guy because right, I only care about I generate new image. Yeah. Then okay, what is this critique network? It's nothing but a denominator, discriminator. What we do is we train a neural network, and this neural network is a classifier. This classifier will give it 2 types of image when training: image from generator and images from real data, training image. So this is fake. This comes with label fake. This comes with label real, right? So the discriminator is to classify whether the input image is real or fake, or real or generated. So if the discriminator is giving a generated image, saying that, hey, this is real, generator will say, hey, I got you. So I will backpropagate saying that I need to remember that when I sample from this sample, I do these naughty things, and then this image will be praised by the discriminator. Okay, that's it basically GAN. And there are some actually. If you look into the loss function of GAN, it's actually solving some equilibrium based on this operation, but this is a very high level view of GAN. I think I will stop this.
Questions on GAN. I'll just summarize it in maybe one sentence. The generator wants to generate pictures, the distribution of which initially, whatever that distribution is, the discriminator will say, I know that the generator's distribution is different from the real distribution. So the discriminator will classify correctly. But if it classifies correctly, generator says, I did not do a good job. So generator would say, let me try to design a new picture that is hard for the discriminator to classify. So over time, if you play a game between these two, in fact, this is game theory. If you play a game between these two, the generator will start to generate pictures that the discriminator cannot classify. And hence, implicitly, the generator has learned the data distribution. implicitly, right? But all of this is happening through samples. Okay, flow in one shot.
The right to think that this approach is totally different than like all the math we've been doing.
Yes,
Okay.
but this approach has beautiful things in it, which is it has now figured out a way to train the neural network as a game. It's a min-max optimization. Okay, the discriminator has to maximize the separation, because if discriminator sees that the fake images and the true images are far away, it's happy, right? Why? Then I can say which is fake, which is real. But the generator is sad, because the generator wants to fool the discriminator. So the generator wants to push the synthetic distribution towards the real, right? So that's a game theory approach. And by training this with this loss function, which comes from game theory, it actually does converges. But you know, here is the big problem with GANs. If the generator generates all cats, great, right? Because discriminator will say, oh, these are all realistic images, or I cannot tell. Sorry, discriminator say I cannot tell. And this is called the mode collapse problem. Meaning, if the real image distribution has modes in cats, dogs, humans, trees, GAN may not learn all the modes. GAN may learn only one mode or two modes and generate only images in those modes. Discriminator won't be able to do anything, and it will be done. The generator will say, I'm doing great. But at the end, when you use that generator for generation, it will only generate cats and dogs. This is the
But over time, like the distributor also learned that most of the fake images that I get are cat images. Like higher probability of cat images being fake. So then it will force the generator to start generating other ones too.
No, but look, if the cat looks realistic,
Yeah.
the discriminator has no way of telling the two.
So because you get images from true training image and generated image, right? So this boils down to a distribution. If from all images discriminator see, all the cats are from generator, only a few, like 10%, is real because 90% is generator always generate cat.
Yeah.
Then discriminator, yes, they will say that, oh, once I see a cat, I will say it's fake, although it's real. Discriminator will tune among that. But the problem is such a tuning may not give information for generator. You see, right? I am lowering your score down not because you are doing bad. It's because you are not matching the real distribution. But generator say, whoa, what can I do? You didn't tell me that where I'm not. I cannot do much. I cannot do better if I modify the cat distribution. You ask me to create another mode, and that's where GAN will stuck. So it's not because mathematically you cannot reach. If you look at the perfect point, the GAN, yeah, if we start from the perfect point, it will reach equilibrium, but it can easily stuck in local minimum. That's what I'm going to say.
Yeah, we'll talk about this. The generator needs gradient to move in the right direction and change. It may not have gradient. We'll talk about that offline.
And generally, the state distribution is better because of that.
100%. 100%.
That's state of the art and diffusion.
Stable diffusion is absolutely state of the art. Okay. So GAN took an image, took a random sample from our noise Gaussian distribution and figured out some way to get to,
PDX.
figured out some way. No. GAN did that, right? No.
Start from Gaussian.
What did GAN do? It started from a Gaussian sample, passed it through the generator, and the generator generated a good image. Okay? That was what GAN was doing. Okay, let me back out and tell you. No, maybe this is, if I start with this, I'll have to go through everything. Okay. In math, there is a way in which if you have a Gaussian distribution in some n-dimensional space, there is a way, very, very precisely written out way, where you can change each of these points to this Gaussian distribution becomes a uniform distribution. I can transform each of these points in multiple steps so that at the end, all these points become a different desired distribution. Does that make sense? So imagine a tray in which there are marbles and the marbles are Gaussian distributed. Okay. Mathematics tells me there is a shaking function, very carefully designed. Okay. Shake that with the first shaking function f1. You shake it. It becomes something. Then math says, shake it with the next function called f2. You shake it. And math can tell you, you shake it with k functions, you shake it k times, you will get a uniform distribution.
I can just take the inverse of x minus it.
Exactly, right? So you need to know that inverse function. Right? You have to design the function carefully. Okay? But because see, you have to do it multiple times.
That's what you asked.
Right.
Otherwise, I can do it once and just like.
Correct. Right? So this is what the core of the mathematics is. I'm going to do a bunch of transformations so that you have to learn the transformations so that the end goal is a desired distribution. So what normalizing flows are going to do is I'm going to start with a Gaussian. Each point is an image in 4,000 dimensional space. I'm going to shake it. And the final one, where do you think the points are? These points, these are marbles in 4,000 dimensional space. I shook it. Where do I want all the marbles to be in the final stage? Where the images are. In 4,000 dimensional space, wherever there's an image, I want a marble to kind of sit at that location. If I learned that functions or that series of functions, what have I learned? I've learned I've learned how to go from one point that the marble was sitting here to some image over there. And not only that, I've learned something beautiful. Tell me that. True. But hey guys, this point over here, when you sample, do you know the probability of that point? You know, for Gaussian you do. So you know the probability of that point. You pass that probability through that function. You still know the probability, it's transformed, but you know the probability. Agree? You pass it through another function, you know the probability. Hey, so what is the cool thing? When you end, you know the
Probability of generated image.
you know the probability of the generated image, which none of the other guys was able to give you. That's beautiful, right? But in designing this, you have to compute Jacobians. This transformation, by the way, is a vector valued function. Why? You give it an input, which is a location in 4,000 dimensional space. The output, you basically shake it, right? So the output is another location in 4,000 dimensional space, right? So the input is a vector, the output is also a vector, right? So if you differentiate this function, this is a vector valued function. So it becomes a matrix, which is the Jacobian, right? So you need a Jacobian, which is invertible, and it's easy to compute, which is hard. And people are coming with creative ways of designing this function. I mean, this function will be learned by a neural network, but you have to make sure that whatever the neural network learns is invertible, and the Jacobian can be computed. That's the hard part. Some people have made some progress, but not there yet. But this has this beautiful tantalizing feeling that if I can do it, I know probabilities of images, which is the holy grail, right? Which is really, really good.
So normalizing flows would be if they work well as good as diffusion plus I get a probability.
Exactly.
Exactly.
Exactly. In stable diffusion, I don't get a probability. Why? I climbed log of py. Even though log of py, right, has the same peaks as log of as px, that doesn't mean the probabilities are the same, right? That's why I don't know the probability in diffusion. Flows, I know the probability as well. Okay? So the flows would basically end like this. You take a Gaussian, so once the flow is trained, imagine the flow has been trained, then you start with a noise, you pass it through each of the transformations, you get an image. And you get an image with probability. That's very good. Why do you want to use how do you use the probability? If you get an image and imagine the flow did not do a good job and that's a bad noisy image, the probability should be low. Right? So you can say, oh, this probability is 0.63. I'm going to throw it because I don't think it's a good image. Generate again. Pick another random sample, generate, you get another new image with probability 0.92. So I'm happy with that.
The process is deterministic once you pick.
Deterministic, right? So every trajectory from here to there is deterministic. Absolutely.
But again, it's not gonna find those nodes that are in your
100%.
because it's gonna, even if it does, it's gonna give you a really low probability.
Absolutely. Creativity and generative creativity and hallucination. This is an art, right? This is, you have to say how much of creativity do you want, how much of no, creativity and consistency is an art. You have to tell, if I'm an artist and you want me to paint a picture, I'll ask you, do you want this picture to be very realistic, like in terms of physics? Or do you want to, can I have liberty to make the eyes go out of the face and whatever creative liberty I want? Right? That's the norm. I think that's an open problem. No one even knows how to formulate that problem.
So I want to step back from everything you've talked full day. And please talk to us. You may have done it at the very beginning, I was there, but so reflect a little bit on GPT 4, 3.5, 5, all these models. And so like, what is your sense? So these things, these techniques you've talked about today, are they not? How do they fit in that world? And you know, I get this last part. I get the probability distributions necessarily keep working on it, but how do they fit in the larger scheme of things that we have today?
So, very nice question, right? Like zooming out, right? Maybe this is a good way to end. So, language is often called a discrete data. Every word is discrete, right? There's nothing like an average between a boy and a girl. There's no word in between. It's very discrete. So this whole GPT model is trained with a different philosophy altogether, which is that it is discrete and you predict the next token, the next word based on the previous word, so on and so forth. So this is all LLMs. This one is much more continuous. If I have an image, if I move a little bit, I have another image. If I have a little bit, move a little bit, I have another image.
So DALI, take DALI as this.
This is exactly that.
So which one of them is the
Diffusion.
VA plus diffusion.
Yeah.
Oh, both.
So DALI is doing diffusion on VA's latent space. So it's called latent diffusion.
Yeah. Okay. So actually, that's a maybe you care about this answer. Yeah, that's a good point, Wally. Sorry, thanks for reminding me. Oops.
So does anybody use GAN?
Does anybody use GAN? I mean, I would say vanilla GAN is not that popular today because it requires we skip that, but it requires a great amount of data compared to diffusion and VA. VA you can see latent space, so it compress, so it is much less data. You describe the rules, right? One way we skip is that, hey, you didn't find the rule, you ask a generative model to directly gen, that requires a lot of data. But a good thing is that, also echoing previous questions, GAN is quite different with VAE and diffusion. It does not like liquid. It jumps out and the mass is completely different. So a lot of work is actually saying, hey, can I plug the discriminator into, for example, diffusion? Can I plug the discriminator into VAE? So you can see something like VAE GAN, VAE some diffusion discriminator. These kind of
GAN is like a guy who can look at a bad image and say this is bad, look at a good image and this is good. So imagine I have a diffusion model which generates an image, but I'm not sure I can put a GAN and say, hey GAN, why don't you tell me if this is good or bad? And I'll use the GAN's knowledge to sharpen my diffusion. DALI, what is DALI doing? DALI is doing exactly this, except for one difference. These are what dimensional, guys? 4,000. DALI says, let's make it latent. All of them are snapped down to 128 dimensions. So it's doing the diffusion in the latent space. Right? Why? Diffusion in 4,000 space is very computationally hard. And in the latent space, you tend to learn rules. Right? In the latent space, you remove noise. If I give you a lot of data and I say compress, you're going to remove the noise and you're going to compress the structure of the data. Right? So latent space will keep the structure and remove the noise, and this final decoding will put back the structure or put back the details of the picture. So latent space plus diffusion is what DALI does today. But then DALI can do beautiful other things. Let me just give you one more example. This was trained with only noise, correct? Now imagine I train a picture with a caption. So caption is also a point in n-dimensional space. Right? Any sentence, if you look at the words, you take all the characters of that whole sentence, that is some point in n-dimensional space, right? So you take a picture in 4,000 dimensions. Let's say the sentence caption is also in 4,000 dimensions. Now you train it together in the 8,000 dimension. Okay? That means every picture is associated to some caption along with it. Right? And now you generate. It will generate a picture, but also give you the caption. It will generate a new picture, but also give you the caption.
So my follow-up question was, which I don't know, is the multimodal models.
Correct.
So they are not trained this way, because here you have a correlation.
Yeah.
Right, or you have a sort of multimodal models are just trained differently, and you have two neural networks.
No. Why are they trained differently?
I'm asking.
No, okay.
The LLM,
So,
let's say,
sure.
say LLM and then image, right? You want to sort of have.
Yeah.
You want to say, show me an image of a
Correct.
basketball.
Correct. So you train every image, you take a caption. Those two are together, right? You download all images from the internet, and whatever is the caption below that in Google.
But let's say if they're not together. I get it together, but if they're not together, you want to create it.
Yeah. So
You want to generate a new image through a description that you have given.
Right.
So now you have two. One is
If they're not together,
like they don't come together. They're not trained together.
So today, this is what at least GPT 3.5 do. I'm not sure about 4.0. 3.5, they say that they specifically train GPT when they are saying that, hey, give me an image. If they receive this kind of request, they will generate a prompt that is fitting DALI. So it has a DALI as its backup engine, image backup engine. So my ChatGPT will say, you were saying that, for example, you are saying that, hey, please give me a picture of Ramen teaching a course. So he will generate, in the backend, he will generate a sentence called generate realistic Indian man with black t-shirt giving lectures with PowerPoint in a large lecture hall. Because DALI, they need super specific descriptions. And DALI, they train on a super large image with caption data, but not this kind, so that he can break all these descriptions into text. I need a man, I need an
My
image.
question is that the models trains, when they say multimodal models, are they trained separately?
that's not how it goes, Victor. The DALI model, when the image is trained, if you want to query it with a prompt, you have to train the diffusion model with the caption.
DALI.
Okay.
Look at GPT-5 scenario. That's going to be a multimodal model. So what are they going to do? It's just one training sequence, which includes, because you said that in LLM, for example, the words and all have no meaning. Like you gave an example, right? And then in images, it's a little different. So now, is there a way to combine the two? Is what I'm asking.
This is the only way to combine, which is, if this is the dimension of images, that line is 4,000 dimensions, imagine, right? To be able to combine, you have to create a dimension of caption or text. And now every point, if this is 4,000, this is 4,000, this is 8,000 dimensional. And every point in this is not an image, not a caption, but something together. Okay, so now you train this model. And now what you're saying still holds. Now suppose I have a separate LLM and I ask, give me a cat with a red hat. Okay, that's the caption I give it, cat with a red hat. It gives me some value over here because this point is exactly the caption cat with a red hat. Now look, for this caption, all these images, that's the distribution, right? All those images are cats with red hats, right? So you take this distribution, you go to gradient descent on this distribution and you say, okay, you stop here, you take this image and you return that as cat with a red hat.
Okay, thanks.
But there is still, I think, yeah, that's one example. But if I'm thinking about LLMs or transformers training, for example, instead of reinforcement learning in GANs, right? So they start with videos of GANs. And so they're not giving you one point, actually looking at the temporal correlation with the next. Right. In that sense, it's interesting. I mean, you made a difference between discrete models, which are LLMs, and then continuous models, which are pictures. But here we have both. Because you want to go from one image to another, and there is a temporal correlation, which is.
But he's convert. You go ahead. I think I
So
understand.
this is a different one. Yeah, I agree. In this case, it's one-off, right? But I'm talking about transformers which are actually doing like gameplay. Or I don't know what multiple models do. I don't know how to do this. But even
But at a very abstract level, Bozidar, can't we have another axis on top over here, which is time?
But yes, if you learn based on the language, but they don't, right? But at least I've seen one demo where they actually learn based on videos. So they see a character playing in the game, moving left and right. And based on these, so they have a recording of where you move left and right and what actions they do, and then the images they see, and they train on that. So it's not like two where you kind of train separately, Stable Diffusion separately, and seems they're trained together, but I don't know.